Hello! This video is for Module 2 Part 1 and includes a discussion of an introduction to cross-validation. Okay, let's go ahead and get started then. A regression model was used to obtain predictions in Module 1. The data used to evaluate the predictive performance of the regression model was the same as the data used to build the regression model. To best understand the predictive ability of a model, the evaluation of the model performance should not be based on the same data as was used to build the model. Cross-validation is a process in which data is partitioned into two groups. One group is used to build the model, and the second group is used to evaluate the predictive ability of the model. In my opinion, cross-validation should be used anytime predictive analytics is being done. Okay, let's talk about the types of cross-validation. For simplicity, let's just assume that all of the observations are placed into a hat. The first type of cross-validation that we are going to talk about is called split sample. Here, the data is just randomly divided into a train set and a test set. So if all of my observations in my hat are here, I'm going to randomly identify some of them as my training set, and the others are going to be identified as my test set. We are going to use the training data to build the model. So we're not going to use all of the observations to build the model. Instead, we are going to use a subset of the original set of observations. We are then going to evaluate the model using the observations that were not used to build the model. So when I take my data and divide it into groups like this, I use one group to build the model and the other to evaluate the model. That is called cross-validation. In the example that I have here, I have split the data into what we call a 75-25 split. So 75% of my observations will be used to build the model, 25% of my observations will be used to evaluate the model. Variations to these percentages are common. Sometimes we'll use an 80-20, sometimes we'll use a 2/3, 1/3 split. And to be honest, the split or the proportions in each split really are not that important, and it has to do more with just one's preference. In this scheme, or in this setup, the predictive performance of a model is measured using only a subset of the observations, and in particular, it's the observations that are contained in the test set. Our model metrics that we have been using, including R-squared, RMSE, and mean absolute prediction error, are still going to be used here. These are going to be computed on the observations in the test set. Okay, so split sample again is when I take my data and divide it into two pieces, a training set and a test set. Let's talk about k-fold cross-validation. In this situation, the data is divided into folds or groups. It is common that each fold has about the same number of observations. So instead of dividing the data into two groups, data is divided into 5, or here in this example, 5 folds. It doesn't have to be 5. You could do 7, you could do 10, you could do 4. Okay, it's just that the data is divided into or partitioned into k distinct folds or groups. The folds are just another name for groups here. A predictive model then is built using all folds except one of them. So we're going to build a model using, let's say, 4 of the folds. The predictive performance of the model is evaluated using the fold that was withheld from the model building step. So in this schematic right here, I have 5 folds. I'm going to remove the 5th fold from the model building step. So I'm going to build the model using these observations from the first 4 folds. But then I'm going to evaluate the data or the model using the 5th fold. And then how we proceed is we are next going to remove the data from the 4th fold, set that aside. We're going to build a model using folds 1, 2, 3, and 5, build the model using this data, and then evaluate it using fold number 4. We're going to continue that all the way through until all folds have had an opportunity to be predicted. Okay, so what I mean by that is in the first iteration here, fold 5 was in my testing set. In the second iteration, fold 4 was in my testing set. I'm going to continue that all the way down till fold 1 is in my testing set. So if I'm doing a 5-fold cross-validation, I'm actually going to have to fit 5 different predictive models. One without fold 5, one without fold 4, one without fold 3, without fold 2, without fold 1. Okay, so most often the value of k ranges between 5 and 10. We may increase the number of folds to maybe 15 or 20 in some situations, but there's really no reason to go larger than, say, 15 or 20. Even if I have millions and millions of observations, I do not need more than 15 or 20 folds. A total of k predictive models are constructed here in this process. The predictive models are going to vary from one fold to the next. We'll see this in an example that we'll see down below. One nice thing about k-fold cross-validation is it ensures that predictions are made once for all observations. So all observations have an opportunity to be in the test set. This is not true with the split sample. With the split sample, I'd randomly divide the data into the training and the test. This observation right here is in the train set, so it is not going to be used in the evaluation of the model. It's going to be used in the evaluation of building the model. Excuse me, it's going to be used to build the model, but not in the evaluation of the model. So not all observations have an opportunity to be in the test set when I'm doing split sample. When I do k-fold, again, all observations have an opportunity to be in the test set. Again, we're going to use things like R-squared, RMSE, and maybe those things are computed on each fold. So I'm going to have a collection of 5 of them. I'll have those values from fold 5. I'll have those values from fold 4 all the way through fold 1. So what we do at the end is we usually average these outcomes across all the folds to obtain an overall measure of predictive ability. There is another one that I'm not going to cover here in this introduction module, and that is called the Monte Carlo. And what the Monte Carlo is a split sample, okay, where I take my data and divide it into 2 groups. But I don't do it just once, I do it many, many times. So Monte Carlo is a method in which the split sample cross-validation is repeated, maybe like 1,000 times, or maybe 500 times. Again, the number of times that I repeat this process is really not that important. In practice, rarely do we use more than 1,000 or maybe 5,000. Okay, but again, even if I have lots and lots and lots of data, it does not mean that I need to perform Monte Carlo simulations, or excuse me, cross-validations across, hundreds of thousands of times. 1,000 is a good number in practice that is used. The predictive model is built using the training set from each iteration. Again, the test set is used to evaluate the predictive ability of the model. Those R-squareds, RMSEs, and mate values are computed for each iteration. And again, the outcomes are averaged over all iterations to obtain an overall measure of predictive ability. Okay, there is one more variation that I'll mention just quickly here, and that is that some predictive analytic algorithms require that a test set be included in the model building process. In this case, a training set is used to build an initial predictive model. Then the predictive model is tuned using an intermediate test set. So what I mean by tuned is it might be improved or might be changed slightly. In the machine learning algorithms, there is a step that is called tuning the parameters. And in those procedures, you might need a train, validate, and test set. So what do I mean by the test set or the validate set? That is the intermediate test set that is used in the model building process. The model building algorithm typically iterates between the training and the validation set. Once a final model has been obtained, okay, then I can measure the true predictive ability of my model using my test data. Okay, so visually, what does that mean? Instead of having just two groups, I'm going to have three. I'm going to have a train data set, I'm going to have a validation set, and I'm going to have a test set. So I have three different colors here. I'm going to use the train data to create an initial model. I'm going to look at the performance of that model using my validation data. Okay, and that looking at the performance and then making a change to the model is called tuning the model. So this is an iterative process here. Once I have what I've determined to be my final model, I'm going to move forth and test that final model or evaluate that using my test data. This does partition your data down further, so you're going to likely have less observations in your test set and your validation set than if you were to just have two groups. But again, some machine learning algorithms require this set of three sets, I guess, in order to complete the model building process. Some general comments. Cross-validation is widely used when doing predictive analytics. In my opinion, all predictive models should be evaluated using cross-validation. Most cross-validation methods require that more than one predictive model be fit. And this is actually a good thing. The inherent variation that exists from one model to the next tends to actually improve the overall predictive ability of the model. Another thing that cross-validation helps with is the idea of overfitting data. If I'm going to use the same data to fit a model and evaluate it, you may fall into a situation where you overfit the data. And when you overfit data, it actually does not do well when you're trying to predict for new data. So cross-validation tends to prevent overfitting of models. Okay, let's implement a cross-validation in an example here. The example that I'm going to use is just out-of-pocket costs for 36 patients. We've looked at this data previously. I think it was on a homework assignment. Here's what the data looks like. Okay, I have the age and cost. So my response is going to be cost. My predictor is just going to be age here. I have added a row for observation there because I'm just going to need to keep track of what observations belong in my training set or my test set. So the other information that's in this data set is not actually going to be used. The sex, BMI, or smoker is not going to be used here. So what are the steps here with a split sample cross-validation? The first thing I need to do is randomly divide the data into two partitions, into a training set, which is going to be used to build the model, and a test set, which is going to be used to evaluate the predictive ability of that model. Step 2 is to build the predictive analytics model. Step 3 is to evaluate the predictive ability using the test set. Okay, so how do I go about partitioning the data? Well, the first thing that I'm going to need to do is to create a list of labels. Okay. Now this data had 36 observations in it. So I have a row here labeled 1 to 36. If I take 75% of 36, so if I do a 75-25 split, that means 27 of the labels should be identified as train and 9 of the labels should be identified as test. Okay, now I've done that here in this column. Okay, so there's going to be a total of 27 train, and the bottom here just contains my test set. I am then going to get a set of random numbers. The only reason I'm going to get a set of random numbers is just so that I can randomly sort or distribute these labels across the 36 observations. Now, you can do this real easily in a spreadsheet. You just use the equal ran function, and that produces a random number between 0 and 1. Then what I did is I actually took the random numbers and the group and I sorted them by the random numbers. So over here, the random numbers have been sorted. I start with 0.06, I go to 0.085, I go to 0.048. Okay, I don't know where 0.048 is at in this list. There it is. That's actually a train. So again, I take the random numbers and my labels that I have here, and I sort them by the random numbers. And what this is going to do is simply rearrange my labels in a random order. So my observation number 5 is going to belong to the test set. Observation number 10 is going to belong to the test set. 13 is going to belong to the test set. And so on and so on. There should be 9 of them listed here in the test set. You do not want to just identify the first 27 observations as train and the last 9 as test. We want to randomly assign the group to the different observations here. Once I do that, I can create in my original file a column for group. Okay, so now I'm going to use this data to do my modeling. With this group column here, I can just filter out the data when I'm doing my model building, and I can just filter out my data by test when I'm trying to evaluate my model. Okay, so that's how to partition the data into two pieces. The next step then is to build a predictive analytics model. And I'm going to do this fairly quickly because this is information that was covered in Module 1. I'm initially going to consider just a scatter plot of age versus cost. The black line is a straight line model. The gray here is actually a curve. Okay, a model that curves a little bit, and that actually looks like it performs a little bit better than the straight line model. But I'm going to just start with a straight line model. So cost is my response. Age is going to be my predictor here. I go ahead and fit that model. It looks like it's doing pretty good. I have 98 R squared. Here's my actual cost versus predicted. That looks pretty good. But when I look at my prediction errors versus predicted cost, I notice that I have a pretty distinct pattern here. When the predicted cost is low, I tend to overpredict. When the predicted cost is real high, I tend to overpredict. And when the predicted cost is in the middle, I'm actually overpredicting here. So under on the edges and overpredicting in the middle. One thing that'll help alleviate this pattern or take care of this pattern is by adding a squared term to my model. So a polynomial type term. So that's what I do next here, is to fit a polynomial type model. And when I'm looking at my actual cost versus predicted scatter plot, it looks a little better. The prediction errors versus predicted costs looks much better. See, I don't have that parabola pattern anymore. And we're evenly distributed about the prediction error equals 0 line. So this model, I'm confident, is going to do a good job. The R squared here is very, very high, 99.67%. Here's what my predicted cost equation looks like. I'm just going to use these estimates here to obtain that equation. Again, it has age in there, and then it has an age squared term. The next thing then is to measure the predictive ability of this model, not against the data in the training set, but against the data in the test set. So that's what I've done here. Again, you can see that this is all my test data. Observations 1, 2, 3, and 4, if we go up here and look, observations 1, 2, 3, and 4 belong to my training data. Observation 5 belongs to a test set. So again, when I'm getting my predicted cost, I'm just doing that on the test set. Observation 5, 10, 13, 23, on down. There should be 9 of them in here in my test set. I'm going to get the predicted cost and also the prediction errors. I'm going to use my 3 measures, as I talked about, in evaluating the predicted performance. The first being the R squared, which is simply the correlation between the cost and predicted cost. And then I just need to square that correlation. I could get my RMSE. My RMSE involves taking the squared prediction errors, averaging them, and then because I squared them, I need to take the square root of that information. Now this is just in essence one measure of the average error. And then the one that's a little more intuitive is to just take the absolute value of the errors and then average those. And that's the MAPE measure that we've talked about in Module 1. So I have 3 measures here, R squared, RMSE, and MAPE, that all can be evaluated on this test set of data. Those values are 99.97, so quite high. My RMSE here is 257 and my MAPE is 246. Now it is likely that the RMSE and maybe even the R squared and such are going to be a little bit better for the data that was used to build the model. So my RMSE up here is 245.5. My RMSE in my test set is a little bit higher at 257. Now that is expected because the test set, the data in the test set was not used to build the model. Excuse me. So this measure here, these measures here, again, are a better truth in this model's ability to make predictions. Okay, let's talk about k-fold cross-validation. It's going to be much of the same. The only thing that differs is how the data is partitioned into the k different groups. Here I used a 4-fold cross-validation. So the step 1 then is to create labels for each of the folds. You can see that here, fold 1, 2, 3, and 4. I have a total of 36 observations, and I have 4 folds, so 36 divided by 4 is 9. I'm going to need 9 fold 1 labels. I'm going to need 9 fold 2 labels, 9 fold 3, and 9 fold 4 labels. We usually try to keep the number of observations the same in each fold. I once again go get random numbers. I can do that using a spreadsheet. I sort those random numbers from smallest to largest, and what that's going to do is simply arrange the labels randomly across the observations. So here, taking this information that I have here and putting that back into my original data, I can see that observation 1 should be put into fold 2. Observation 2 and 3 should be put into fold 1, etc. down the line. So all 36 observations will be assigned to one of the folds. In my model building, what I do with k-fold cross-validation is I withhold one of the folds or groups from the model building process. Okay, so don't use one of the folds to build the model. A predictive model is constructed using the data from the remaining folds. Then the predictive ability of that model is evaluated using the data or the fold that was withheld from the model building process. And then I need to repeat that for each of the folds. The same model structure is often used on each iteration of this process. However, that isn't necessary. So here I'm going to fit my quadratic or polynomial model for each of the folds. For fold 1, here is my predicted equation. My r squared, when I withheld fold 1, this is the model that I got. So this model right here was built using data from fold 2, 3, and 4. This model right here was built using data from fold 1, 3, and 4. When I withheld fold 4, so this model down here at the bottom was constructed using data from folds 1, 2, 3. I'm going to use this first equation when I'm trying to predict or make predictions for fold 1. I'm going to use this second equation when I make predictions for fold 2 all the way down. I then can get my r squared, RMSE, and MAPE values from these predictions. So I can get those values, again, r squared, RMSE, and MAPE, when fold 1 was withheld. I'm going to make predictions for the observations in fold 1, and then here are my metrics for those predictions. I'm going to make predictions for fold 2, okay, and those are the metrics there. And I'm going to do that across all folds. So I have 4 different models. I'm going to have 4 different r squareds. Okay, now this r squared right here is not the r squared from the model building step. This r squared was computed from the observations in fold 1. This r squared here, it's not any of these up here, but instead this is the r squared, which is the correlation between the actual cost and predicted cost for the observations in fold 2. This RMSE right here, okay, does not match any of these up here. No, this RMSE is computed from the predictions that were made for fold 3. Okay, and those quantities are averaged to get us an overall predictive ability of the models. So here you can see that I retain a fairly high, very good R-squared. I retain about a 250 on my RMSE. This is within $250 here, so that's really good. Or if I'm looking at MAPE, I'm within $220 here. So these quantities here are averaged to obtain. This here is obtained by averaging the R-squared across the 4 folds. Okay. The task here involves answering, looks like 5 true-false questions and then 3 open-ended questions. That does it then for an introduction to cross-validation. Thank you.